before we leave this page, one more issue to remind you. As I mentioned already, by cascading, we can enhance the output resistance by this and that factor. So if your supply voltage is high enough, yeah, you can sacrifice the headroom to get better output resistance, right? So is it possible to do double cascading? I mean, cascading here and cascading there, right? Here you can enhance by 100 times, and wow, okay, if we have large enough supply voltage, is it right? No. Why not? Because I warned you already, RE prime. Okay? That is RE prime instead of RE. RE prime means you need to consider this factor. Okay, so you can see, yeah, for this one, no good, then we have the first cascading, very good. But how about second cascading? Because the output resistance is already sky high. Okay, even that is infinite. So what is the impact? You get this for RE prime. Okay, it doesn't make any sense. You sacrifice one more headroom for nothing, because RE prime right now is limited by HIE. Okay, don't expect you can get another 100 times increase in output resistance. No, I promise you, after calculation, the output resistance will be almost the same as single cascading. Yeah, so you had better learn everything smartly. Some say, oh, cascading, by cascading we can increase the output resistance by 100 times. Don't remember anything like this, no. You need to know exactly why, all right? Otherwise, you will get many kind of misunderstanding to destroy your own lives, your future lives for analog IC design, okay? This is also, the class is much different from NTU or from NTNU, from everything. I try my very best to let you know what you need to learn, and to warn you what kind of misunderstanding don't get. Okay? Again, we don't have any kind of mathematics, no. That is simply waste your time and my time. All right. And then for such kind of cascading, actually we have quite many different structures. For example, Wilson current source. You can see, yeah, if you, because I told you, the most important issue is to increase the output resistance, right? How about here? Who cares? For output, they don't care. We don't care. So this is almost the simplest structure for cascading. Okay? You can get almost the same output resistance. Yeah, you can do any kind of calculation. And again, this is already learned by yourself from microelectronics. Wilson current source already existed. Okay, so that's it. But what will go wrong if you drop this transistor? What will go wrong? Okay, allow me to show you. I told you, even Q1 and Q2, you do your very best to match them. They are almost the same. I cannot say they are exactly the same for analog IC designers. Please, nothing will be exactly the same. No, nothing. Okay? Even though you do your very best to make them almost the same, what's the impact for your current mismatch? One is beta, right? The other one is what? Early effect, according to your VCE, right? So VCE here and VCE there, will they be the same? No, right? Because VCE1 is almost 0.7 volt higher than VCE2. Okay? So no accurate current matching you can get with such kind of Wilson current source. Again, again, I highlight a very important idea for you. You get something supposed to be, you will lose the other. Okay? You can say, hey, you cannot say, hey, I take advantage. I just drop one more transistor to get better performance. Usually not. Okay? You gain something. Yeah. You save one more transistor, then you lose something. For what? Current mismatch. Okay? Anyhow. Yeah, anyway, that is what I told you already. And how about RO? Derive it by yourself. As a student, I derive almost everything. Okay? Not only for all those equations, but also the examples and then the exercise from number 1 to the number n, from the beginning to the end, everything. Okay? Yeah. Oh, even though I graduated from the best EE in Taiwan, NTUST. Okay, for microelectronics, 3 semesters. Each semester I got more than 90. Okay, and then after graduation, I think my overall ranking is 20 among 170 something. So I'm really proud of my microelectronics. I'm not so stupid, right? Yeah, about 10%. In NTUST. But when I taught here, I was totally surprised. I suddenly figured out I almost knew nothing. I know how to derive equations, but how about the logic thinking, the operation principle? No. Yeah, that is really upset. And this is the reason why I force myself to fully understand, because to teach my students, before that, I need to convince myself all what I teach my students should be correct. All right? So even my performance is really good. I mean, when I study my bachelor degree, but I still need to confess, I don't get good enough understanding about the operation principle. And how about you? To be a very good IC, especially analog IC designer, you had better refresh all your mind about microelectronics. Even during your learning about analog IC design, the most important issue is still the concept, the operation principle, instead of the equations. Equations are only used to convince you all those operation principles, all those statements on the textbook are correct. That's it. Okay? Yeah, anyway, except for very few cases, for example, LNA, that is really simple. You can derive something. PLL, because we study a lot, we pour a lot of effort to construct all the models. You can do good enough simulation. For most of the, and then maybe OPAMP, okay? For all the others, forget about it. How about ATC? How about DAC? How about, no. Nothing, almost nothing you can derive, okay? Yeah. And then, let's go for the other kind of current source. We call it Wheeler. Wheeler current source here. What is the major idea? You can see, again, even Q1 matrix Q2, but VBE equals VBE1 equals VBE2, and then VRE, right? So VBE2 is supposed to be much smaller than VBE1 if you have a very large resistance here. Okay? So what will be the impact? You know, IC or IE equals I as exponential VBE by blah, blah, blah. If this is reduced, then the current will be substantially reduced according to exponential decay. Okay? It means what? The current here and the current there will be a huge difference. But why we need such kind of Wheeler current source? Simply because, yeah, we would like to get very small, very, very small output compared to the input. Okay? This is a very efficient way. Later, I will show you the traditional way to get larger or smaller current. But compared to the traditional way, this one is much, much more efficient. It means what? You don't need to sacrifice a lot of chip area, yeah, to reduce such kind of upper current. Yeah, they can differ maybe in 3 order, 4 order. I mean, yeah. Oh, yeah, anyway, piece of cake. Simply increase the resistance of RE. You can make it. Okay? Okay? But again, well, it is so efficient. What is the disadvantage? Again, much more mismatch after fabrication you need to face. That's it. Okay? That's it. Because, allow me to point out that on chip, for our design, I don't think you will design anything of chip. We hope we can integrate almost everything on chip. But for such kind of on-chip resistor, capacitor, blah, 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 usually you need to face mismatch after fabrication, I guess, at least 30%. Okay? See? 30% here after exponential, blah, blah, blah. How much variation here? Not 100%, 200%, no. I guess hundreds, even thousands of percent in deviation. Okay, yeah, maybe not so scary, but I need to promise you, much, much larger than 30%. Can you afford such kind of variation? Usually not. Okay, that is what I need to warn you. Even though, oh, this is a very simple idea, you learned it already from microelectronics, you can apply all those old knowledge from discrete to integrated version. No. Many of the concept, many of the knowledge for discrete world is totally different from our integrated world. Okay? Don't do anything, simply copy and paste. No. Unless you know what you are doing. What do I mean? Unless you get the exact idea. You know exactly the operation principle. Yeah. And then you can do everything you like. Okay. It is so inefficient because from the first page here now, we only talk one-to-one. One input, one output. It doesn't make any sense because for our own chip, we have a lot of blocks. And for each block, for each sub-circuit, you need to bias them, right? And again, on chip with bias current instead of bias voltage. Okay, you need to generate a lot. Then only one-to-one, not good enough. Then we will talk about multiple current sources. Okay, this is the idea. Yeah, one-to-one, or too many ones. That's it. All right. You say, hey, again, this is the advantage with this. Oh, we call it bias network. Okay. Yeah. It means what? Bias network means a sub-circuit to help you generate all bias current or bias voltages you required for the whole chip. Usually we call it bias network. But even this is some kind of common name, common terminology. Even you only have one-to-one, sometimes we still mention it as bias network. Okay, so anything, if you heard anything about bias network, it means the circuit to help you generate usually bias currents for all the others. Okay, or for the others as you like. Yeah. Anyway, right now, with such kind of multiple current sources, one for all, in theory, one bias network can generate all those currents you need, all those bias currents you need for all the other sub-circuit. Oh, it looks really nice. That is the benefit. But what is the disadvantage? Again, you need to sacrifice something. right? Right? What you need to sacrifice? What's that? I help you to highlight already. Here. Again, one for all means the bias current needs to be supplied by this branch. It will make much more deviation for your IREF from the other output current here. Okay, you can see if n equals 9 or 10, then you will get around 10% deviation from 1% to 10%. Are you happy? If not, then you may, how can I say, use the current attenuator here, right? Yeah, another transistor, as you like. I don't care. Yeah. So after you get good enough understanding, then you had better memorize all those important skills, cascoding, current attenuation, blah blah blah, for your own future. Okay. And then you will say, hey, you cannot suppose all your sub-circuits will get exactly the same bias current. No, it doesn't make any sense. Usually, your sub-circuit, for all those sub-circuits, they consume different bias currents. Okay, so what you can do? For example, how can you generate 1 to 3? 1 to 3 output current. Oh, piece of cake, just like this. Okay, this is the traditional way. 1 to 3. How can you make it? 3 unit output current sources connected in parallel. Okay? Why? Accuracy. Okay? That is what you need to sacrifice. Yeah. From microelectronics, maybe Smith or the others say, I don't care, I don't mind. What you learned, what they said, yeah, in their textbook, they say, hey, look, if you would like to, never mind 3 times larger, n times larger, yeah, they say, wow, yeah. Such kind of ratio current, right, can be generated by emitter area design. Oh, what do I mean? If you would like to get 3 times larger output current, you don't need to connect 3 in 1, 3 in parallel. No, only 1 with 3 times larger in emitter base area. That's it, good enough. Okay, just like this. The same base, the same collector, only the area between base and emitter is increased by 2, increased by 3, increased by n. Okay, that is what I duplicate, I copied and paste from microelectronics. But, yeah, only for fun. Allow me to show you a very famous commercial ad. Okay, maybe years ago, I have no idea whether it still exists.
In Mozambique, the Inhaminga tribe believe that if a man is skillful enough to capture a lock of a lion's mane, then his own hair will grow back. The younger men watch on, learning from afar, as their brothers stalk the lion with great stealth and exceptional precision, knowing that the slightest error could prove fatal. There are many myths about regrowing hair, but for a proven way to help stop or slow hereditary hair loss in 4 out of 5 men, get Rogaine.
That is a so-called unfounded legend. Okay, 不可靠的传说、传言。Yeah, not only for commercial ad. Okay, don't expect you cut the lion's hair, then your own hair will be grown back. Yeah. If you don't believe in that, don't believe in this. Okay? No. It's totally incorrect. No. I'm not criticizing the content of such kind of microelectronics. No. Because they live in the past. Okay? I mean in discrete era, it is correct. Okay? Maybe not so correct, but I cannot say it is wrong for discrete era. However, for integrated circuit, it is totally unacceptable. Okay? With such kind of idea, I promise you, the mismatch will become sky high, will become too high to be acceptable for usual applications. If you would like to make 1 to 3, 1 to n, 1 to anything, that is the only way you can do. To get enough accuracy, enough precision for such kind of current ratio, please. Yeah, that is the the most fundamental idea. 1 to n means n transistor, yeah, to the output. That's it. No other way you can do, unless you would like to do calibration. But calibration usually takes a lot of time. Time means money. Okay, if you wouldn't like to have any kind of calibration, very complicated circuit design, blah blah blah, then that is the easiest way. Yeah, 1 to n, 1 at the input, n to the output. That's it. Oh, but that is the most fundamental one. You still need to apply common centroid layout, blah blah blah. Oh, yeah, 这只是基本款哈，还要做同重心布局，有的没的。Anyway, again, unless you know what you are doing, otherwise, don't simply copy and paste anything. Okay, the idea in discrete era usually cannot apply to integrated era directly. No. Okay, again, don't make any misunderstanding. Yeah. Then we can go further. You may say, hey, for our circuit, they not only consumes n-type current, it is sinking. You sink. So like what you go to the toilet, you wash your hands, then there is a sink. Yeah, to sink all the current. We call it current sink. 洗手的时候，洗手那边不是有个东西叫尾驴？In Chinese, yeah, it is. It's really amazing. If I'm right, it is called this. Because from ancient China, yeah, that is sink. Okay. Anyway, if I told you this, not only foreigners, I guess 100% of the local students, they have no idea what's that. Actually, that is sink. Okay. The formal name in ancient China for sink. Till now, yeah, for professional workers, they still call it. Okay. Anyway, don't care. We have n-type current source. It is, we call current source sink, and also p-type. We call it, yeah, output current source load. Yeah, anyway, sinking or sourcing. Sometimes we call it sourcing because you push out the current. Okay, as you like. Then, in this way, you can see the bias network can help you generate, according to current mirror, 1 to 1 to 2, right? For n-type. And then 1 to 1 to 3 for p-type. I think like many kind of composition as you like. And then you can control, this is very important. Through here, IP in theory will equivalent to IN, right? Right? Because they are connected in series. Your current should be exactly the same as mine, blah, blah, blah. Roughly speaking. In this way, we can control very good accuracy among all those n-type, p-type current sources. Okay? Bingo. That is what you need for your bias network design on chip. But even till now, there is still something missed, because I only told you how to generate 1 to 1 or 1 to n, right? N is an integer. So it means what? Right now we only told you the way to generate larger current sources. How about smaller one? Just like this, right? I told you, it's no good, it's no good. Inaccuracy, you will cause a lot of mismatch like this. So how to generate, for example, this one, 1 to 1 over n. Anybody? Any idea? How to make it? Much smaller. Yeah. Pardon? In what? In series? It could be, but not exactly. It could be. Okay? On the contrary, okay, yeah, that is a very good quiz, a very good test, first test for you. If you get good enough understanding, supposed to be you need to know how to make it. For example, 1, 2, 1 over 2. How can, yeah, the hint is already here. See? The hint is already here. Yeah, exactly. This is what you need to do. Okay? Yeah. If how much state, yeah, it means 1 here and the other 2 there connected in series, right? But I told you already, the above one and the bottom one, they won't be exactly the same. So in this way, it is possible, but you will get a lot of mismatch. So John's version is the traditional way. Okay? It means 2 or 3 connected, yeah, diode connected to generate smaller one. So as you like, to enlarge or to reduce the output current, that is the traditional way. On chip, for integrated circuit, if you concern very much about the accuracy, about the current ratio, please, this is the only way. But again, that is the most fundamental requirement. After that, you need to do good enough layout pattern, okay? And also the size of the transistor cannot be too small according to random mismatch. And how about systematic mismatch? 1 to 2 or 2 to 1. You need to have 1 to 1 or 2 1 2. Yeah, it depends. Yeah, 2 to 1 current source or 1 to 2 current source, as you like. Okay, to amplify it, to attenuate it, as you like. Okay. So right now, I help you to refresh your mind for humankind's history in BJT current sources. How long? It took tens of years at least. Okay, even only within 17 pages, but humankind, I guess, all those circuits I show you, I guess it took more than 17 years. You can see how slow the progress in analog IC design. For digital one, each generation right now, I guess, take around 1 year, okay? From 7 to 5, 5 to 3 nanometer, and 3 maybe right now the limit is predicted as 1 nanometer, okay? That is what I learned from the web. Anyway, let's go to our own era most. Because right now, BJT is almost out of the market. Yeah. So again, application basic. You can see most of the structure actually we duplicated from the BJT version, but with some kind of modification. Again, it's really seldom you can simply copy and paste from this to that without any modification. Really, really few. Yeah. don't do it. So again, yeah, what is the application? The same. What is the ideal current source? Yeah, the same. Okay, yeah. And how about current biasing? Why? This is a very good explanation. If you would like to get any kind of bias voltage, then you need the help of such kind of so-called voltage division, right? How to divide voltage? The easiest way is through the help of R string. That is another very good, very important terminology for analog IC design. R string, 电阻串. Okay, it means resistors connected in series, just like a string. That's it. So this R string for what? Usually for voltage division, 分压，电阻串 for 分压. Okay, that's it. But as you may already know that, I emphasize again and again, resistors consume a lot of area. It is noisy. And also that, from VDD to ground, it conducts a lot of current. It doesn't make any sense, right? It is noisy, it is money wasting because it occupies a lot of chip area, and also power wasting. Forget about it. On CMOS chip, we usually apply such kind of current bias instead of voltage bias. Okay, keep this in mind, and then we can go further. Yeah, anyway, for such kind of M1 and M2, yeah, 1-to-1, okay, from the beginning, simple, very simple current mirror. Congratulations, for what? Look, we can take the advantage of the gate current because the gate is totally isolated from the channel. Instead, B to E actually, it needs to be forward biased. So it conducts IB in BJT. But right now, IG equals 0. So what is the advantage? We don't need to worry about the bias current. It means the mismatch between I out and I reference can be reduced. Is it correct? From this aspect, yes. But totally, no. Why? Again, you get advantage here, you need to sacrifice the other. What you need to sacrifice? Sorry for that. Yeah, that is the ugly truth. 丑陋的现实。Okay? 有所得，必有所失。This is reduced. That's it. Okay? We get some benefit there, but we lose something here. The output resistance of MOSFET actually is much lower, much smaller than BJT. What does it mean? How much you can get, you can expect from this? Usually 10K instead of 100K. Okay? Usually one order less in output resistance. It means what? Yeah, the slope is 10 times higher, yeah, compared to BJT on average. Okay? And again, how to match the current? Yeah, just like this. I out, I in, yeah. It depends on the aspect ratio of 2-to-1. Okay? But again, you say, hey, how to generate 2 times larger, 3 times larger? Because, hey, in theory, I just increase the aspect ratio for the output for most factor 2, right? Yeah, is it correct? No. Again, totally incorrect. Yeah. In theory, that is right. In practice, no. Yeah, that is what I told him. Very good, but yeah, again, RO is no good. You can have some kind of very simple derivation, and finally you get this, right? Okay, forget about it. Yeah. Anyway, for output resistance, you need to consider what? Channel length modulation. I told you already, so you have this term, I have that term. To match the output current to the input, you need to promise me, even though they are supposed to, no, they are not supposed, they are assumed to be identical, exactly identical. Even with such kind of assumption, you still need to promise me To make I/O totally equals to I reference, you need to promise me the VDS2 needs to be exactly the same as VDS1. Otherwise, it doesn't make any sense. Okay? You need to promise me the voltage here and the voltage there should be exactly the same. However, that is in idea. In practice, I would like to provide you such kind of current bias current as you like, right? But I told you, hey, be careful. Your voltage should be exactly the same as there. But that doesn't make any sense because the output voltage is not decided by you. No. Output voltage is supposed to be decided by what? By output load itself. You just provided me the current, then how much voltage I need. That is my business, not yours. Okay? If you control my current and my voltage, I promise you, with 0%, you can get for application. No application will allow this. And then the other idea you also need to know, for each node, for each branch, you can control either voltage or current, but not both. Okay, that is already proved. Maybe not in theory, but by some kind of practice or some kind of measurement. Anyway, that is the fundamental knowledge about our circuit. For output, again, I need to highlight it. For output, you can control either voltage or current, but not both. All right? No circuit on earth can do anything like this. Okay? Okay? So it is impractical. Nothing behave like this. So again, to be the current provider, your promise is, okay, how much is the output current? And then don't expect the output voltage will be anything you like. No. It's not decided by you. It's decided by your load. Okay? Only by chance, decided by them, and wow, lucky enough, for some reason, it is the same as that. Congratulations. You can neglect this term. Otherwise, usually not. Okay? The output voltage usually is not the same as here, as your input node. Forget about it. Yeah. Anyway, that is the ugly truth you need to face. If you would like to consider the second order effect, I told you, yeah, many kind of error. Yeah, not only in, okay, that is for practical concern. Even though you have this ideal equation, you will say, hey, if I make this and that the same, and the voltage the same, lambda 2, lambda 1 the same, then I can get exactly the same input and output current? No. Because the real equation should look like this. Mobility 1, maybe even C oxide 1, C oxide. Yeah. Everything after fabrication cannot be exactly the same as you predicted. Nothing. Okay? So you will have variation in mobility 1, mobility 2, C oxide 1, C oxide 2, VTN 1, VTN 2, lambda 1, lambda 2. All of them. And also, I warn you, don't expect VDS2 will be exactly the same as VDS1. Wow! That is what you need to face. You have more problems than, how can I say? Usually we have, yeah, you have more unsolved problems than solved problems. Okay? That is what analog IC designer needs to face almost for every case. Okay? 你阿未解決嘅物件，絕對比你解決嘅更加濟就對啦。Okay, yeah, unstopped ones are supposed to be more than stopped ones. Okay, but anyway, it can ensure your own future because, maybe I mentioned already, for Intel chip, digital one occupied more than 90, right? For analog one, maybe less than 10%. But they hire more than 50% of the analog IC designers to solve less than 10% of the problem in analog domain. So it means what? If you get good enough understanding, then you can secure in the future nobody, they all fire you. Okay? Yeah. They need to respect you more, they need to pay you more, blah blah blah. Anyhow. So how to control that? Again, not only for this, but also for mobility, for lambda, blah, blah, blah. Again, the best policy is to use replicas, 复制品. Okay, you duplicate 1 to 2 to 3 to 4 to make everybody look the same. Not only in circuit, but also in layout. Okay, that's it. Replicas, a very important idea for analog matching. Yeah, this is a very, very good example for you. Yeah, if you would like to consider, if you would like, no, you need to face not only the first order, but also any kind of second order effects. But how? Don't derive. No. Just face the consequence, okay, by simulation. More exactly, by Monte Carlo simulation. Okay, you need to know, as an analog designer, you need to know how to do good enough Monte Carlo simulation. You need to control for not only process variation, but also for random mismatch. Again, I need to warn you, even though you know everything about Monte Carlo simulation, I still need to highlight that one piece of the pie is missed. That is systematic mismatch. Okay? After fabrication, don't expect your result, your final outcome will be exactly the same as what predicted by your Monte Carlo simulation. It will be worse than that. I cannot say much worse, but it depends on how good you do for your own layout. Okay? Anyway, yeah, let's see what you can learn from this slide. For example, you would like to have 1 to 4 output current from the input. Okay? And see, this is some kind of simulation done by, not myself, sorry for that, from the other professors. Okay? Oh, yeah, anyway. For example, you can see, according to our equations, just like this. Okay, so in theory, only if the aspect ratio for M2 is 4 times larger. I don't care you have this one or you have that one as you like. I don't care. In theory, they are exactly the same. They are exactly the same. Okay, in theory. Oh, but in practice, which one is better? Anybody? You have 50% to be right. Choose one. Anybody? Which one? I mean, in practice, in theory, they are exactly the same according to the equation. But in practice, which one is better? That is also a very good test for your logic thinking. Which one is better? The above one? Yeah, sure. Yeah. But why? Body effect. Okay. Anyway. For this one, they are connected. Again, they are connected in parallel. For that one, usually you need to connect in series. Okay. And for the top ones, they will face more body effect. They are not the same as the bottom one. So again, for connection, in parallel or in series, usually I recommend you in parallel, unless you cannot make it. Otherwise, parallel connection for analog circuit is better than series connection. The major issue, the major concern is what? Body effect or the other second order effect. We have a lot of them. All right? Hopefully, after my teaching, you will become totally different from the others. Okay, hopefully. Because I try my very best to push my concept to all of you. Hopefully, you get all the points. I do my best, but you need to do yourself. Do everything. Do your best at your side. Okay, so you can see, right now, we have 4 times larger in width. The same L, right? The same L, but 4 times larger in width. Okay, after many kind of simulation, you can see, for example, wow, that is what we need, right? I out. The most important parameter for such kind of current source. Wow, 6% in deviation. It doesn't make any sense. Too bad. Okay? And then you will say, okay, we do something. See, what's the difference? Anybody? What is the difference from the second, from the first to second? Huh? We increase the area, right? We double the width and also the length, right? Not only here, but also there. Yeah, anyway. I told you already, right? Since this one is increased by 4 times, doubled. The width is doubled, the length is doubled, the area is increased by 4 times, so the standard deviation is decreased by 2 times, blah, blah, blah. Wow, almost, you see, from 6% to 2.0, almost 50% in reduction. Very close to this, right? Okay, I need to remind you, this is not done by me. No, I only get the slides from my friends or from foreign professors. I just ask for help. I was a lazy guy, I need to admit. Okay, but anyway, I do my best for interpretation to preach you in which way you can get the best knowledge. Okay, so it makes a lot of sense. And then we can go further. You can see, see, from the first to the second, you sacrifice 4 times in area, 4 times increase in overall cost, right? But you only reduce the mismatch by almost 50%. Then let's look at this. The same, right? And how about that? It means the same 4 of them connected in parallel. That's the meaning. So how about the area? In theory, this and that the same. Right? Right? But you can see, wow! Wow! You get better performance, better accuracy. You don't sacrifice the area, right? From here to there, in theory, you don't sacrifice any more area. But in practice, a little bit more, but not so much. Compared to this one, 4 times increase in area, but the result is not so good. You can see this is the best among them, right? So that is the power of knowledge. If you get good knowledge, if you get good enough understanding, logical thinking about the operation of the circuit, I promise you, that is not any kind of mission impossible. You can see almost no increase in area. You sacrifice a little bit in area for such kind of parallel connection, but you can reduce the mismatch substantially. I told you, always if you would like to get something, you need to sacrifice the other, right? But this is a very good example. In theory, you don't sacrifice anything, but you can still enhance the performance. Why? Through the power of knowledge. Okay, you get good enough understanding, you don't need to sacrifice anything. Okay, that is what you need to learn. That is what you need to force yourself to behave in this way. So again, replicas, keep this in mind. Never mind for 1 to n or n to 1, blah, blah, blah. If you would like to control accurate ratio, believe me, okay, replicas is the only way for you. Don't try to tune the W, the length. No, it doesn't make any sense. But I'm talking about critical devices. If the ratio is really important for you, then the only way is to duplicate the transistor, the devices. Never mind transistor, resistor, capacitor, inductor, emitter. Okay, tutor ABC, no good. Don't duplicate tutor ABC, otherwise you will be shoot by them. If you mention anything, ABC, no. Tutor, no. Doesn't make any sense. Okay, that is our system. Okay. Yeah. This is what I warn you. I preach you again and again. Replica transistor, replica any kind of devices will be the best for such kind of accurate ratio. And again, hopefully you don't use any kind of minimum size, visual size. Again, for critical devices, because the smaller, the more deviation. I warn you already. And then we can go further. Yeah. This is a very simple current source, but lambda is not so good here than early voltage in BJT. Okay. And also that you can see according to I out. Yeah. As you already know, this is trial region, that is saturation, and after that, we have breakdown. Okay? So, according to G out, output conductance, you can see, to stabilize your output current, hopefully the conduction is the minimum. So, according to G out, here and there, no good for you. Only the value, the minimum area, is what you need to have. Okay? So that is the so-called saturation. And again, tell me, what is the condition for saturation? On and off. Yeah, here need to be on, and there need to be off. Okay? Please keep this in mind, because it is really important for you to have the first-hand guess whether or not your circuit operate properly. Usually, for all those MOSFET, they need to operate in saturation region. Usually, but for some cases, not. Anyway, you need to have the power to estimate for each transistor whether or not they operate in triode, in saturation, or in weak inversion, blah, blah, blah. Okay? That is the first help you can get from yourself. Train yourself to estimate in which region the transistors operate. Okay? Very, very important one. Anyway, now you have a lot of current ratio, geometric ratio. I mean this, okay, but no good. You need to apply applicas, blah, blah, blah. Anyway, the problem is what? R is not high enough compared to BJT, so don't expect I out equals I reference. No. All right? So again, what you can do? Oh, we learned something from BJT cascoding. Again, this is for the behavior is current buffer. Keep this in mind. All right? I think almost no professor on earth will tell you this is a current buffer. Okay? And again, who controls the current ratios from I ref to I out? Who controls the current? Those two. Okay? Why I need to preach you again and again? During simulation, if you figure out something wrong with the current ratio, please, the first help you can do is to focus on M1 and M2. Okay? There must be something wrong for your sizes, for your bias, yeah, or even for your layout. Because after layout, you get a lot of parasitics. Okay? If the ratio is incorrect, first of all, you need to focus on this. Instead of that, okay? They have the second, I cannot say they have no impact on your upper current. No, they still have some, but much, much less than this one. So to myself, I called them, for such kind of current sources structure, current mineral structure, I call them current controlling transistors. 控流电晶体，电流是由它们决定的。Okay, and what's that for cascoding? But again, M1 for M4 for cascoding. How about M3 to provide bias for M4? That's it. Okay, so we call it self-bias, self-bias. The easiest way for self-biasing is to apply diode connection. To connect it just like a diode I mentioned already. Okay, that's it. Yeah, with such kind of self-biasing, you don't need to apply. Yeah, it saves a lot of money and effort for you. You don't need to apply anything like this. That's it. They can generate proper bias by themselves. You don't need to help them calculate. Don't need. You don't need. Why? Okay, just like this. I had better explain something more for you. For example, if the VTH is too small from the beginning, too small means what? The current from here will be less than that, right? So according to KCL, Kirchhoff current law, yeah, some of the current will flow in this way. To charge the capacitor here, so the voltage will be increased. Until what? Until stabilization, equilibrium. After stabilization, no current will flow into this node, right? So it means the current will be exactly the same as I read. That's it. It can fine-tune the bias voltage by itself. So we call it self-biasing. Okay, that is a really important idea for analog IC design. By what? Diode connection. If not, then somebody needs to do something. And hopefully, don't call help from resistors. That's too noisy, power wasting, money wasting. Okay. But who can help? Yeah, later I will show you how to generate proper bias without the help of resistors. Okay. Yeah, anyway, let's go further. Yeah. So, cascode current source. The simple idea, again, yeah, by this, see? Here, the original resistance will be increased by what? By this factor. See? Please pay attention to what I mentioned moments ago. I told you it will be increased by my own GM and my own RO. Keep this in mind. Never mind in BJT, in MOSFET, because according to small signal analysis. You can see you will get this. Okay, okay, almost the same. If we neglect one here, the second issue I need to warn you is what you learned moments ago. For such kind of cascoding, you can only apply once. Don't apply the second time, the third time for BJT. No, that is really bad. But again, don't tell me, I learned something from BJT. It is not allowed for double cascoding, triple cascoding, blah, blah, blah. So it is not allowed here. Are you sure? Are you sure? Why? Why? Yeah, sure. So the major difference is from the gate to the source, actually, it is broken. It is open circuit. But in BJT, you have HRE, right? Right now, we don't have anything like this. So congratulations. As you like. You can apply the second cascoding or even the third cascoding if you have enough headroom. Yeah, I mean high enough supply voltage. Okay, here to there with cascode, you can increase the output by GMR4 RO, usually again 100 times to order increase. So if you apply the second time, another 100 times, bingo, at the expense, at the cost of larger headroom. That's it. Okay, are you happy? Again, don't get any kind of misunderstanding. Yeah, in BJT, maybe it is not allowed, but here it is allowed. Okay, yeah, or in BJT, it is functional, but here it doesn't work. All right, simple copy and paste from this domain to that domain. No. So to play safe, the best way for yourself is to get fully understanding instead of derive anything. No. Usually for students, after derivation, it takes a lot of time. You become really exhausted, so you get nothing. Okay, what's wrong for test, for grading? That's it. Okay, just like what I did when I was young. Okay, but I didn't get any kind of full understanding about this. That's really upset. Yeah, anyway, that is the most important issue I need to show you. Between gate and source, nothing existed. Congratulations. You can apply cascoding again and again. However, according to process evolution, the VDD goes down instead of goes up very soon, right? So, in practice, double cascoding or triple cascoding, I think it doesn't work anymore, especially for new processes. You need to be very careful. Even for single cascoding, maybe it doesn't work at all for 7 nanometer, 5 nanometer, unless you use thick MOSFET. Otherwise, it doesn't make any sense for you. Okay? Yeah. All right. To help you go further, go deeper. That is what I need to show you. But before that, I need to confess. For the whole slide, I help you to make only 2. The first and the next. Only 2 slides were prepared by myself. For all the others, from my friends, from the other foreign professors, from my friends anyway. So please pay much more attention to those 2 slides. Why I need to help you prepare these 2 slides? Simply because I think they are very important. Yeah, I hope I can help you to get even better understanding than all the other professors. Okay? Yeah. Anyway, what I would like to preach you is For such kind of self-bias, the so-called diode connected MOSFET, like PMOS or NMOS. This is for NMOS, that is for PMOS. Okay. But anyway, I only explain NMOS. For PMOS, similarly, think by yourself. Okay. Then, first of all, you can see diode connected means the drain is connected to the gate directly, so the drain should be off. How can you make it on for NMOS? The voltage difference between gate and drain needs to be 1 VTH higher. So it means the drain needs to be 1 VTH lower than the gate. Otherwise, it cannot be on. It should be pinched off, right? Right? Right now, you are the same. No worries. It is off. To make it functional, VGS should be on. Don't tell me VGS is also off. What kind of circuit you have? Yeah. But anyway, it is possible. For what? Leakage. Okay? I need to tell you again. In the past, most of the, maybe almost all the designers, they say, hey, off here, off there, it doesn't make any sense. No. Ridiculous. It doesn't make any sense. No circuit would like to get both VGS and VDS off. But right now, many of the engineers turn their head away from such kind of traditional structure to make them both off. For what? Leakage current. Okay? To make the circuit operate in leakage region instead of triode, saturation, weak inversion. No. Simply cut them off. For what? Power saving. Yeah, especially for IoT, for human sensor, for environment monitoring, because it is very hard to power all those devices. Yeah, IoT. Why you have millions of IoT devices on campus in the city? If you would like to power them by wires, right? It will make the city very messy, very dirty, and it's really expensive. So hopefully, yeah, we can power them by battery. One battery for 10 years, good enough. Okay, but you need to promise me the circuit consumes very, very little power. Right now, low power design become a very important issue for the market. In the past, we only focus on high performance. High performance always means high power, right? But right now, low power design is really, really important. And the technologies for high performance design and low power design are almost totally different. Okay, so for the engineers, they focus in very much on power. How can I say, on high performance design, high end design. If they would like to turn their head away to low power design, they need to retrain themselves. Okay, because all the technologies, most of the techniques, I mean, cannot be applied at least directly from high end to low power. No, really, really different. Okay. Yeah, but how about this one? Usually, if you don't operate in leakage region, then it should be on. On here, of there, usually, I promise you, it works in saturation region. It has no any kind of possibility to operate in trial region because this is off. For trial region, both need to be on, right? So diode connected is no good. No. It never operates in trial region. Okay? Yeah. But not only for saturation region, that is the so-called strong inversion, right? If for VGS here, it is about to be off. I mean, you cut it to be only VTH. In theory, the current will be 0, but in practice, no. That is the so-called weak inversion. Okay, so 2 possibilities. Oh no, 3 possibilities for that kind of diode connected transistor. Strong inversion, that is the usual case. Then weak inversion, yeah, to enhance the gain, but with very slow operation speed. Then right now, leakage for what? Very low power, extremely low power. I'm talking about nanowatt instead of microwatt. Right now, microwatt is not good enough for such kind of low power operation. We push ourselves very much into the era of nanowatt. Okay? Yeah. Yeah, and again, I need to highlight here how much is the difference. VTH plus delta V. Okay, and how much is delta V? Okay, a very good explanation here. Oh, sorry. Delta. Okay. Yeah. So, delta V means what? The difference between your VGS and your VT. Okay, because VGS needs to be larger than VT. By how much? By delta V. Okay, that's it. So after derivation, okay, delta V here. See? This is, I hope this is what you need to memorize. Okay, the property. A very good and simple for you to memorize here. The delta V of the so-called VD saturation, VDS saturation, is proportional to what? The square root of L over W. Okay? Why I need to highlight it? Because usually it is contradictory to your how can I say, intuition, right? Intuitively, 直觉上, most of the students or new designers will think, the larger W over L, the smaller delta V. No, on the contrary, it's incorrect. Under what? If ID, if the bias current is fixed. But I told you already, that is the usual case. Okay, your bias current is decided already from the beginning and generated by bias network. So the bias is fixed, bias current is fixed. If you tune it, because it is fixed, if you tune it, then it means this one needs to be lowered, right? Right? But I have squared here, so delta V, the difference between VGS and threshold voltage, I mean VTH or VT, should be reversely proportional to the square root of L over W. Okay? Keep this in mind. It is not, no. It is reversed. Okay? Please keep this in mind. Because later, we need to apply this very important concept. And then we can go further. Never mind for diode connected or non-diode connected. If you would like them to operate in saturation region, then what is the minimum voltage you need to apply? Okay? Yeah, anyway, for diode connected, I told you already. For example, for MOS, they are the same, right? And here, from VG to VS, right? You can be lower by 1 VT and 1 delta V, right? Right? Got it? This is very important. And how about drain to source? The same, because they are connected together. I mean source and drain, gate and drain. Okay, that is for PMOS. That is for NMOS. And how about PMOS? The same. Okay? I mean, but it is reversed. It is flipped. So from here to there, the same. 1 VTP, okay, and 1 delta V, lower. Okay? Again, from top to bottom. I don't care. It is NMOS or PMOS. And then If it is not diode connected, that is the usual case. Most of the transistors, they don't have such kind of diode connection. And how can you operate them? I mean, for the usual case in saturation region. So for MOS, you will know from G to source, from gate to source, again, 1 VTN, 1 delta V, right? 1 threshold voltage and 1 delta V, right? And how about drain? Uh-oh, that is another story. Because to make it in saturation region, this need to be on, that need to be off. What is the definition for off? Again, gate here, right? How to make it on? The source need to be 1 VTH lower than the gate, right? But that is in trial region. Right now we are talking about saturation region, so you need to be higher, at least 1 VTH lower. You need to larger than or equal to VG minus 1 VTH. Got it? Got it? So it means what? For saturation operation, please keep this in mind. Get full understanding. For drain, it is allowed to operate 1 VTH lower. The minimum is 1 VTH lower than your gate voltage. But no further lower than that, no. Greater than or the minimum equal to 1 VTH lower than VG. Okay, keep this in mind. And how about VP? How about PMOS? The same. The drain voltage according to gate, it can be increased. It can be higher. The maximum is 1 VTH. Okay, got it? Got it? Okay, so what is the critical condition? The extreme condition. The gate need to be 1 VT and 1 delta V higher than the source. But the drain can be 1 VT lower. So the minimum voltage between drain and source to operate in saturation region is delta V. Got it? The same there. Hopefully, yeah. Through the help of those two slides, you will have better and easier design in the future. Okay? So we can go further with the help. If you get the point, I promise you all my students will be much better in such kind of design, especially to estimate the operation region. Yeah, how much your circuit can survive, can be functional. The minimum supply voltage needs to be how much? Okay? So for example, for cascading, for such kind of cascade current source, to estimate how much, okay, from here to there, 1 VT, 1 delta V, right? And it is connected to here. And again, the other VT, the other delta V. So here, 2 VT plus 2 delta V, right? And then, how about the output voltage? What is the minimum output voltage? I told you, the drain to the gate can be at the most 1 VT lower. Not much lower than that. So the minimum operational voltage for your V out is how much? This minus 1 VT. Congratulations, 1 VT 2 delta V. Okay, this is what I promised your cascade current source can operate. But how about simple current source? If you don't have this, the output here, what does it mean? Delta V, right? So this is what you need to pay. One cascade cascading means 1 VT more for your headroom. If you would like to do how can I say double cascading, you need to sacrifice 1 VT more. Okay, but more exactly, not only 1 VT more, 1 VT plus 1 delta V. That is, more exact number you need to pay. So for double cascading, 2 VT, 2 delta V, too much, to be honest, for practical concerns, for practical applications. All right? Are you happy? If you ask me if something wrong or when necessary, you need to push your output voltage lower than this, what will happen? This one will become on. Here will be on, there will be on. So M4 will operate in trial region. Okay? And you need to be careful. Cascoding is only functional. For what? All of them need to operate in saturation. Okay? If they are not operate, any one of them doesn't operate in saturation region, no cascoding at all. The cascoding mechanism is destroyed. So right now, without cascoding, you only get what? Because this one is already on in trial region. Okay? But that one is still survivable. Yeah, only if you have delta V here, M2 can be happily stay in saturation. So you have very good RO2 here, right? But M1, M4 is already on, both on in trial region. In trial region. So you have such kind of R on 4. It is on instead of off. So R on 4 is much less than RO2. Okay, so this one much less than that one. But the slope is inversely proportional to your output resistance. So right now, your resistance becomes smaller, your slope becomes larger. Okay? And then you push it even further. So what is the limit for this one? I told you already, delta V. And also, I need delta V. If it is lower than 2 delta V, then not only you are on, but also M2 is forced to be on. Trial region, so you have R2 plus R4. That's it. Congratulations. Okay? Again, almost nobody on earth will teach you in such kind of detail. Most of them, they derive equations for you, but I'm exceptional. And hopefully after my teaching, you all will become exceptional analog IC designers. If you get all the points, okay? No need to derive anything, only by explanation, by yourself. You will know. After derivation with equation, I promise you, you don't know exactly how much you can operate and what is the output resistance. No. By watching the equations you derive or the others derive, it's really hard to get such kind of understanding. But yeah, by explanation, piece of cake. Okay, if you have good enough background, good enough understanding, full understanding. Yeah. Anyway, what is the problem with this? Oh, allow me to explain more for such kind of current buffer. Again, current buffer, the major purpose, the major function is to help you pass the current controlled by M2 and M1, as you like. Current controlling transistors. And I help you to pass your current all the way to output, exactly because M4, the gate is isolated from the channel. So ideally or in practice, except for any kind of leakage, okay, 100% of the current here will be there. Congratulations, okay? But that is not the only one function. There is another even better function for you to make sure your I out will be exactly the same as your I reference. Why? I told you already, you can only control either the current or the voltage, not both. Okay, so for us, we'll be more than happy to control the output current, but you will lose the control for output voltage. It's decided by your load, by your output load. So never mind, it is higher or lower, higher or lower. For M4, because the gate voltage is fixed by self-biasing. You provide proper bias to yourself and M2. You for yourself and M1. Okay. So they are fixed. The voltage here and there are fixed. Okay. So in theory, what is the voltage here? Also fixed. Congratulations. Because here and there, one VT and one delta V lower. Right? Right? So how much voltage here? 1 VT plus delta V. Oh, congratulations! Because for M1, the same. Right? You don't have any kind of channel length modulation between M2 and M1. Why? Because M4, the bar will help you to absorb all the voltage difference from your output. Never mind it is higher or lower. M4 as a buffer, they help you to isolate this node. They help you to isolate VDS2 from the output voltage. 100% of the voltage difference is absorbed by M4. M4 sacrifices itself to be the buffer zone to keep you live happily since after M1 and M2. Wow, they can be exactly the same. Are you happy? Okay, so two major issues. One is to pass 100% of the current from M2 to output, and then help you observe the output voltage difference to keep you safe. No voltage variation in theory will be seen here. Perfect. Very, very good. Okay, that's it. No channel length modulation will be seen by M2. Really important idea. But what is the problem? M3 and M4, they face some kind of body effect because their body cannot be connected to the source because M3, M1 all on the same P substrate. So by nature, for P substrate process, that is the usual case. Your body and the body are already connected because they are the same P substrate. Okay, so you have only one choice to connect it to the ground. That's it. So for M1, body and the source are all grounded, no body effect. But how about M3? No. The body is grounded, but the source cannot be grounded, right? You have body effect. I have body effect. So how to reduce the body effect if you are unhappy with that? Here. Again, that is only in theory, okay? In practice, as you like. Yeah, but from the very beginning, usually we have W3, W4 larger than W1, W2. Why? Because I told you already, delta V is proportional to square root of L over W. So if you increase it, then this will be reduced. That's it. Okay? To cancel the impact of the body effect. But it is not so useful. Yeah. I mean, for your real design, do you need to have W over L much larger for M4, M3 than M1? No. To be honest, the first cut for your design, 第一手, what you can do, the same. If you would like to get 1-to-1, I think the same aspect ratio will be good enough for the first cut, for the first guess, and then fine-tune the W over L. That is your boring life. But your future will be secure with such kind of boring design because AI is too talented. Yeah, it is also not so good as such kind of boring work. Okay? Yeah. And then, all right, maybe we can stop here. How to enhance the output resistance even further? I told you already. Single case code, double case code. No. Too much increase in overhead in the headroom. No good, right? So to keep almost the same overhead, what the others you can do? This is so-called improved or self-regulated current source. Actually, it is some kind of negative feedback. All right? Negative feedback. Why I mention this? All right, it's a very easy idea to check, easy way to check. The feedback is negative or positive. So, for example, if for some reason you increase the voltage or you increase the current here, right? Then all the way, the current here is increased. What can you expect? The current there will also be increased because they are connected in series, right? And according to M2, the IV curve looks like this. How can you increase your current? It means what? The VDS needs to be pushed higher by larger current, right? Because the slope is positive. Okay? So the more current you would like to have according to ID2, to the output, then you need to promise me the higher current means the larger VDS. Okay. But the larger VDS here through negative amplification. Negative amplification, it means what? The gate voltage or M4 will be lowered. Wow, what does it mean? Its source voltage is increased, but its gate voltage is lowered, right? So much smaller VGS. What does it mean? The current will be reduced to compensate for the increase of the original tendency. From the beginning, ID2 would like to be increased, right? But after, I told you, again, that is a very good practice for yourself. If something happened to increase it, and this is also increased, and the voltage is also increased, through negative amplification, the gate will be decreased. VGS will become smaller. It means what? The current will also be reduced. So the tendency here and there is totally different. We call it negative feedback. Okay? On the contrary, so don't tell me, hey, look, because this is negative, so it is negative feedback. No. Sometimes it is totally different. Okay? Even you have negative amplification, you still get positive feedback. Okay? So the best way for you to judge which kind of feedback it has is, again, to increase it or decrease some parameter. And after the feedback loop, if you can push it back, if you increase it, then the feedback will reduce it. Okay? If you reduce it, the feedback loop will increase it. Congratulations, that is negative feedback. On the contrary, if you increase it and the feedback will like to increase it further, that is positive feedback. That is the best way for you to assess, to judge what kind of feedback you have. Okay, that's it. So, what is the most important idea for negative feedback? What is the knowledge you learned from your circuit theory, microelectronics? You can sacrifice your gain for almost everything. Okay? The amount of you to sacrifice your gain, how much you sacrifice your gain, will be almost the same for you to enhance all the other parameters. Okay, maybe that is too hard to understand. For example, if you reduce your gain by 100 times, by 100 times of the gain, then almost the other parameters will be enhanced by 100 times. That's it. The stability, the bandwidth, the linearity, almost everything will be enhanced with the same amount. The amount you sacrifice, you gain, will be almost exactly the same. The amount you enhance the others. That is for negative feedback. So, with such kind of slogan, right? What is the gain? Minus this. You amplify. But the gain is totally sacrificed because I told you already, the output current is the most important parameter for current source, right? You would like to increase it, then the negative feedback will push it back. If you would like to decrease it, it will also push it back. So, in theory, it will be constant. The output current will be fixed. No gain at all. I mean AI, for the overall circuit, the current gain will be exactly 1. So you sacrifice all the amplification here, right? But again, that is what you sacrifice. And again, you can enhance almost everything, including your output resistance. So for current source, you would like to enlarge or reduce the output resistance. You hope it can be increased, right? By how much? AV. What you sacrifice will be enlarged here. By derivation with a small signal, blah, blah, blah. Okay, you will get this, 1 plus AV. But I told you, the amount is AV, right? My estimation without any test, any derivation, no one. That's it. But does it bother you? No. Because, for example, you have minus 100, then 100 and 101, no difference at all for practical concern. Okay? You say, hey, look, if it is only minus 10, then you will get, my estimation is 10. And the absolute value from derivation is 11. You say, hey, 10% in difference. I promise you, during simulation, the figure, the deviation is much more than 10%. So again, no difference. Okay? For absolute value, don't believe in equation. Equation is never be correct. Why? Because it's too simple. For humankind, we can only memorize, we can only derive very simple equations. But for our simulation tool, SPICE, especially HSPICE, iSPICE, they use very, very complicated model. Okay? So what you derive and what you simulate, I promise you, at least tens of percent, maybe hundreds of percent difference if you are unlucky. At least tens of percent deviation. So 10 or 11, nobody cares. Okay? I'm talking about estimation. It's very important for analog IC designer instead of absolute value derivation because it never be correct. Okay? Are you happy? So, in this way, you don't, in theory, you don't need to sacrifice your, how can I say, your headroom. You have delta V here, in theory, delta V there. Oh, congratulations, the headroom is 2 delta V. Right? But what is the price you need to pay? Here, more area, more power consumption. Okay? But this is not the only price you need to pay. Yeah. For practical concern, I need to warn you. Input offset voltage will kill the output. Okay? If you apply something, never mind differential or non-differential, for such kind of amplifier, don't expect you have y equals ax. No, usually you have b, offset. And such kind of offset, if you do everything good, yeah, it can be positive or negative with 50%. So if it is the offset is negative, what does it mean? The output after fabrication, for your simulation, you won't see anything related to offset unless you apply a Monte Carlo simulation. Okay? Otherwise, it is perfect. But after fabrication, 50% of the offset will be positive, 50% will be negative. If they are negative, what will go wrong? VGS may be too low to be on, so it will be totally off. Then I still need to say congratulations because you get infinite output resistance. That is what you want for your current source, right? But it doesn't work anymore. It is off, right? So the risk is, if you don't pay attention to input offset voltage, in theory, 50% of the chip were out of the market. The yield were less than 50%. Are you happy with this? No. Only for this 50% off, right? Your chip have many kind of sub-circuits like this. 50% off, 50% off there, so totally 0% for your yield. So another lesson you can learn from this slide is you need to pay attention to every kind of detail during your design. Otherwise, you cannot survive in the future. Okay? It doesn't relate to IQ. It is related to EQ. To be very cautious, to be very picky. Okay? Yeah, that is related to EQ instead of IQ. So again, if you're not so good, so talented in IQ, you can still survive here by hard working and also learning. Okay? All right. I would like to go further, but sorry for that. I have another meeting. Okay? So please keep all those very important ideas, even though they are very basic, very fundamental, very easy, but really, really important for your future. Yeah, how to estimate this. Okay? And then, yeah, those two slides, please go back to have even better understanding. You can forget all the others, but those two slides are really important, especially this slide. Very, very important for you. Okay? To be a very good estimator for your future design, I think you had better get full understanding about this. Thank you all.